Let's look at 3.2. So this is about polynomial functions and their graphs. So here are the objectives. So we are not just using the calculator to look at the graph. We need to identify characteristics such as end behavior, zeros, multiplicities, and then the relationship between degree and turning points. Then we will graph it. So a polynomial function is a function that has an exponent that's greater than 2. So we know that we have the quadratic, which has exponent of 2, and then to the third power is cubic, and then to the fourth, fifth, and so on are just different powers. So these polynomials of degree 2 or higher have smooth and continuous graphs. So an example would be like this, or it could be like that, where they have this kind of crazy looking thing right here. And it doesn't have to be symmetrical, but it is smooth and continuous. The end behavior is how does it go to the left and how does it go to the right. So whenever I look at a graph, I'm going to decide whether it goes up, up, down, down, or up, down. So it's how it goes to the left. Does it rise or does it fall? So if it rises, it goes up. If it falls, it goes down. And then how it goes to the right. So one like this would be falls to the left, rises to the right. So the way that I say it is this is a down, up in behavior. So to the left, it's falling. To the right, it's going up. It's rising. So although the graph of polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left and far to the right. The sign of the leading coefficient, a to the n, and the degree n of the polynomial function reveal its end behavior. So leading coefficient tests. This is what tells us how it is going to rise and fall, going left and going right. So we look at that leading coefficient, where n is your greatest degree. A to the n is your leading coefficient. So we are going to look at a to the n and look at, is it positive or negative? Well, it depends. So like on this one, this is a positive leading coefficient. The coefficient would be 1. Then we will look at n, which is your highest degree. We are going to look at, is it even or odd? And depending on how we answer those, that determines our end behavior.
And n can't be negative,
right? Right. N has to be positive and it can't be a fraction.
No, it said it has to be an integer.
Mm-hmm. Positive. So positive whole number. Okay, so this is examples of how it's going to be, how the end behavior is going to be. So this is if n is odd, if the leading coefficient is positive, then it's going to fall to the left and rise to the right for odd. So this is considered a down-up in behavior. It's falling to the left, rising to the right. It's a down, up. It's going down here and it's going up here. Odd functions are always opposite of each other. Even functions, they will go left and right the same direction. So odd, they are different in behaviors. So opposite in behaviors. So this is falling to the left, so it's a down and up. So odd degree, positive. So how it ends to the right, see how this is a positive leading coefficient? A positive direction would be up. So that's one way to remember it. If it's odd, they're going to be different, but you look at if that leading coefficient is positive, it's going to go in a positive direction in the end on the right. So this one, it's saying the leading coefficient is negative. So it is going to go to the right in a negative direction. And we know that they're opposite, so up, down. How it ends is the direction that our leading coefficient would go in. And then if we have even degree, it's going to have the same in behavior. So if it's an even degree and it's a positive leading coefficient, it's going to be up, up. To the left, it's continuing up, and to the right, it's continuing up. And then if we have a negative leading coefficient, it's going to go down, down. Has the same in behavior for even degrees. So our first example, all we're going to do is describe our in behavior. So our leading coefficient is 1 because it is 1x to the 4. So that means it's positive. And then our degree is 4. So that means it's even. So we have a positive leading coefficient and an even degree. So we would look back over at the previous slide. Even means they're the same, beginning and end. Because this is positive, we're going to end in a positive direction. So this is going to be up, up. So on my graph, I'm just going to do like that. That's the general direction it's going to be. I don't know how it's going to do in the middle, but this is how it's going to end. The zeros are the function. So back in Algebra 2, we talked about zeros, roots, and solutions. And they all represent the same thing, which is the x-intercept. So you can have real roots and you can have imaginary roots, but each real root of a polynomial equation appears as an x-intercept of the graph. So that would be an x, comma, 0. X-intercept is where you have a number for x and a 0 for y. So let's find the zeros of this function. To find the zeros, we're saying that this equals 0. X cubed plus 2x squared minus 4x minus 8 equals 0. So we need to solve. So whenever you have a polynomial function like this, in order to solve it, we're going to factor by grouping. So I'm going to look at this together and then look at this and see if I could factor something out. X squared can be factored out, leaving us with x plus 2. And then these two both have negative, so we're going to factor out a negative 4. And then x plus 2. So when we do factor by grouping, this is what we put in parentheses, x squared minus 4, and then we put x plus 2 equals 0. I'm going to factor even further because this is difference of squares. Because x squared is perfect square and then 4 is perfect square. So this can be written as x plus 2, x minus 2, and then just carry down the x plus 2 equals 0. So see how we actually have this one twice? So we can rewrite this as x plus 2 squared times x minus 2 equals 0. And we're going to see something about the multiplicity in just a little bit, about what that means about the graph and our zeros. So we're going to set each one of these equal to 0. So x plus 2 squared equals 0. And then x minus 2 equals 0. So remember, we're finding our x-intercepts, finding the zeros. So in order to get this by itself, we would take the square root and then move the x to the other side. So x equals negative 2. And it's twice, right? Because we have 2 of them. So if we were to write them out side by side, we would say x equals negative 2 and x equals negative 2. You're going to see that in a minute as multiplicity of 2. Negative 2 is a 0 twice, which you'll see how that shows up in the graph. Then this, when we solve it, it's just x equals 2. So we are going to graph these zeros. So x equals negative 2 and x equals positive 2. So I'm just going to graph those on the x-axis. Those are my 2 zeros. And let's go back to what's the end behavior going to look like? Down and up. Because it's odd. And the leading coefficient's positive.
Please release JB1 and bar.
Okay, so this is odd and the leading coefficient is positive. So we know at the end it's going to go up. Beginning, it's going to go down. So I just put it like that. Is there anything else that I know that I can graph on here? Yeah, the y-intercept. How do you find that? Yeah, whenever x is 0. So f of 0 equals, I plug in 0 here and I come out with negative 8. Okay, so we're going to come back to this. We're just going to leave that there. We'll come back to it. Okay, multiplicity. So this is what I was talking about. If R is a 0 so 0, remember 0 means our x-intercept. If r is an x-intercept of even multiplicity, then the graph touches the x-axis and turns around at r. So multiplicity is how many times that is a solution or an x-intercept. So this has an even multiplicity because of that 2, that's squared. So if we have an even multiplicity, then the graph touches the x-axis and turns around. If it has an odd multiplicity, so this is just one time, right? So this is an odd multiplicity. Then it's going to go straight through, crosses the x-axis at r. Regardless of whether the multiplicity of a x-intercept is even or odd, graphs tend to flatten out near zeros with multiplicity greater than 1. So this one is going to go down. So if you look, this is our last x-intercept. If I went up from there, it's not following my end behavior. So I know that this is going to go down. I know that this is going to go up because if it went down, that doesn't follow the end behavior. So this is going to go up. We know that this is multiplicity of an even, so that means that it's turning around. So this is going down. And at some point, it's going to turn around so it can go back up. And the way that you'd find that is you could try out, like if I plug in a 1, what would I get? What I ended up doing was putting in a y equals to look at what my point of, that would be considered a vertex because it is turning direction. So we would put this in x to the third power plus 2x squared minus 4x minus 8. And whenever I graph it, I can look and see where that point that it turns around at. And it's right here. So it looks like it's probably at 1. So let's see what 1 is. I'm going to look at the table. So it looks like 1 is at -9. So it's right here. And then 2 is at 0. So it turns around. So looks something like that. It's not perfect, but you know, it'll work. Okay, let's look at the next example. Finding zeros and their multiplicity. So let's look at this function right here. So we look at the exponents to determine their multiplicities. So all of this is being multiplied. So we can set each one equal to 0. So -4x plus half squared equals 0, and x minus 5 to the third power equals 0. To solve this, you would divide by the -4 all the way through to get rid of that, which would still be 0. Take the square root. And what x really is right here is just -half. But this has an even multiplicity. So that means at -1/2, it's going to touch and go the opposite way. It'll go up or down to it and then go the other way. Then the next one would be x minus 5 to the third power equals 0. So x equals 5. And The exponent is what tells us what kind of multiplicity it is. So this is odd multiplicity. So the next slide shows you how that's going to show up on a graph. So we have x equals -1/2 is a 0 of multiplicity 2. That came from here. Multiplicity of 2 is even. So it touches it and goes the opposite direction. It doesn't go straight through it. That's where it turns. Even multiplicity turns at x-axis. But at an odd multiplicity right here, because it's to the third power, it's going to just cross through. But what it said was as your exponents get larger than 1, the flatter it becomes. If it was just to the power of 1, it would go straight through like a line. But to the third power, it's going through. If you look at it like this, do y'all remember what the cubic parent function is? Remember how it looks? It looks like this. Up, down, up, either one. And then squared, this one's a squared. If we just look at that section, that looks quadratic to the second power. Okay, the intermediate value theorem says you look at whenever x is two different values and then see if there's a solution between those two numbers. So you're going to look at f of a and compare it to f of b. If they're different signs, that means at some point it went through the x-axis. If they're the same sign, then that means that it didn't go through the x-axis. So let's look at the next one. So it says f of x equals 3x to the third power minus 10x plus 9 has a real 0 between -3 and -2. The way we show that is by looking at f of -3 and f of -2. So we could just plug in -3 for x. So this is 3, -3 to the third minus 10 times a -3 plus 9. So just use your calculator to find what that is. So I plugged in a -3 and got out 42. -42. And then we plug in a -2. So I'm just going to go up here and change that 3 to a 2. Whenever you plug in the -2, you get 5. So that means that it changes signs, and so it's going to go through our x-axis. So think about in a graph, if I'm at -3 right here, and it goes down to -42, it's right here. But then at -2, it goes up to 5. So that means that there is a real root between -3 and -2. So I'm going to write that here. Different signs means there is a real root between x equals -3 and x equals -2. So somewhere between those is my real root. So if they're the same, that means there's no real root between them. So let's say you get that these were both positive, then whenever you graph them, so I'm going to graph with, so let's say we're doing f of 4 or something like that, and it comes out here, and then f of 5 came out right here. There's no real root between 4 and 5. So in order to determine how many turning points there are, you would look at your degree, which is n, and subtract 1. So the example f of x equals 3x cubed minus 10x plus 9. We would look at our degree of 3, and so we would say it has 2 turning points. Because you take whatever the highest degree is and subtract 1. Okay, let's see, graphing a polynomial function. So whenever you graph it, you're going to look at a couple different things. You're going to find in behavior. Then you're going to find, I'm going to highlight it, in behavior, x-intercepts. And then you're going to graph your x-intercepts. And then find your y-intercept. And then look and see if there's symmetry. And then look at your number of turning points, maximum number of turning points. Okay, so we are going to determine the in behavior here. So we need to multiply this all out to find our leading coefficient, but there's actually a shortcut. Whenever I multiply this, I just want my leading coefficient and my leading degree. So this is going to come out as 2x squared. But then I need to multiply times x. So times x. So our leading coefficient is going to be 2x to the third power. If you would rather multiply everything out to find out what your leading coefficient, you can do that. But I'm telling you, a shortcut would be multiply this number times your x, and then you're going to either square it or cube it, and then multiply it times the next variable, which would just be x. So that's 2x cubed. So we know it's positive. And we know this is odd. So remember, odd means that they're different. Positive means you're going to end with an up. So that means it's going to go down to the other side. So it is a down, up. Okay, the next part is find your x-intercepts. We already have this, so we're just going to set each factor equal to 0. So 2x plus 2 squared equals 0, and then x minus 3 equals 0. And really, we don't need that 2 because whenever we divide, it's going to go away anyway. And then when you take the square root, it's going to go away. Do you know? So it's x plus 2 equals 0 once you get rid of the squared and the 2 that's being multiplied. So that leaves us with x equals -2. And then this has multiplicity of 2, which is even.
How'd you get rid of the 2?
Out front, you divide, if I divide both things by 2.
0 about 2.
Right. And then the squared, you take the square root of 0, which is still 0. Then this one's going to just be x equals +3. And this is just multiplicity of 1, so it's odd. So it's going to go straight through. So I'm going to go ahead and graph it on step 4. So -2 and positive. 1, 2, 3. So those are my x-intercepts. I already have them. F of 0. So that means I need to plug in a 0 for x into my function. So that'd be 2 times 2 squared times a -3. So you do the square first, so that'd be a 4. 2 times 4 times a -3, which is 8 times a -3, which gets us -24. So my y-intercept is 0, -24. So I went by 1s on here. But on the y-axis, I can go by 2s. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So that's my y-intercept. And remember how it's going to end? It's going to end like this. My end behavior. So that means I know this is going to go down like that because multiplicity of -2 means it turns directions. And this one is going to go up like that. And how many turns does it have?
2.
Yeah, 2 turns. So we know it's going to go something like this. Not sure where it's going to turn here, but we can use our calculator. just going to do it like that. It might be that it turns completely around right there. Not sure. So you can use your calculator to look at that. Okay, I'm going to record these two and just put it on Blackboard for y'all. Since we didn't finish, these two aren't very long, but I figured let's just wait till tomorrow. Okay.